Welcome. Hey there, science fans, where numbers tell the story behind every experiment. Accurate measurements are crucial, whether it's a doctor checking blood sugar or a scientist testing water for lead. Chemists repeat experiments not just for fun, but to ensure their results are reliable. But what if one measurement looks way off? Is it a mistake or a clue? This is the challenge, separating good data from bad. We'll explore two essential tools: how to spot and handle outliers, and how to use calibration curves to turn raw measurements into meaningful results. Outliers are those odd numbers that don't fit in, and calibration curves help us decode what our measurements really mean. These methods transform chemistry from guesswork into science you can trust. Thinking like a chemist means questioning results, checking your work, and using smart methods to build confidence. By mastering these skills, you'll see how statistics make science powerful and precise. Ready to uncover the secrets behind the numbers? Let's dive in. In real experiments, results aren't always identical. Tiny variations are normal, but sometimes a measurement stands out dramatically. That's an outlier. Imagine measuring water's boiling point. Your data points are 100.1, 99.9, and 100.0, and suddenly 108.2 degrees Celsius. Whoa, that last number is suspiciously high, a classic outlier. Outliers can skew averages and lead to wrong conclusions. They might be caused by mistakes like a contaminated sample, or they could signal something unusual. Scientists can't just ignore outliers. They need a fair way to decide if they're errors or important findings. Throwing out data without reason is bad science. That's why we use objective statistical tests, not gut feelings, to handle outliers. The Grubbs test is a common tool for this job. It helps us decide if a data point truly doesn't belong. Outliers matter because they can change the story our data tells. Handling them correctly keeps our science honest. Next, let's see how the Grubbs test works in action. If you like learning about chemistry for fun, or regardless of why you clicked on this video, subscribe. I will provide a link to the textbook down in the description below. This textbook is the source of all my videos and lectures, and where the information comes from for my analytical chemistry videos. Let's continue back to the lecture. The Grubbs test is a scientist's referee for outliers. It checks if a suspicious value is too far from the rest to be trusted. Here's how: calculate the mean and standard deviation of your data. Find how many standard deviations the odd value is from the mean. This is the Grubbs statistic, G. If G is bigger than a critical value from known quantities on a table, the point is likely an outlier. In our boiling water example, 108.2 degrees Celsius would almost certainly be rejected. This keeps our results accurate and fair. With outliers handled, we can trust our averages. Now let's see how we use data to build powerful tools in the lab. Chemistry often means finding patterns between two measurements. When data points scatter around a line, we need a precise way to draw the best fit line. The method of least squares does just that. It finds the line that minimizes the squared distances from all points. This isn't just guesswork, it's a mathematical guarantee. The result is an equation, y equals sine mx plus b, that describes the relationship. The slope and intercept reveal key details about our system. This best fit line is the backbone of the calibration curve. Let's see how it works in practice. A calibration curve links a known property, like concentration, to a measurable response. To build one, prepare standards with known concentrations and measure their responses. Plot these on a graph. Concentration is on the x-axis. Response, which is typically absorbance, is on the y-axis. Use least squares to draw the best fit line. This is your calibration curve. To find an unknown, measure its response, absorbance. Find that value on the y-axis, move across to the line, then down to the x-axis. That's your sample's concentration. Always use several standards and check your curve is straight. Never guess beyond your data range. Calibration curves turn raw measurements into reliable answers. With these tools, you're ready to think and experiment like a chemist. Like and subscribe. Make sure to share if you found this useful. Be sure to have a nice night, and good night.